Okay. So it says identify each function as growth or decay, state the y-intercept, and then sketch the graph. So first of all, the first thing we should be saying is this is an exponential growth factor. So our b value is larger than 1, so it's growth. 7 is greater than 1, so it's growth. Then it says what value tells us that. So this is kind of answering that question. It says, why do you know it's exponential growth? So we just say because 7 is larger than 1, it's growth. All right, and then it says, find the y-intercept. The y-intercept is always when x equals 0. So let's plug in 0. We would have 1/3 times by 7 raised to the 0. Remember, any base to the 0 power is 1. So that would be 1/3 times 1, which is a third. So our y-intercept is 0, 1/3. You would do that by hand. Now, when we're graphing this, we really can mostly type it into our calculator, but understanding since there's no shift up or down, we have a horizontal asymptote at 0 here, and then we just said our y-intercept is over 0 up 1/3, so it's going to be right here somewhere, and then we could just go off to the side and plot some x, y points. So if you type it into your calculator, you get some x, y points, another point on the graph. So over 0, we said up 1/3. 1 is up at 2.3, not a pretty decimal, but it's okay. And then over -1, up 0.04, so up a little bit. And then let's maybe graph one more. 2 is clear up at 16, so that's off my graph. So I think those 3 points are the only ones that fit on the, well, then it's getting smaller and smaller. That's the definition of an asymptote, but we know it's growing up like that, and then down like this, approaching the asymptote. Therefore, our domain from left to right is -infinity to infinity, and our range is it's coming in at 0, growing up to infinity, not including 0, because the definition of an asymptote is a value your function will never cross. So we've answered the question. So right here, we would say this one is decay, because 1/2 is less than 1. Our y-intercept we would do by hand. It's when x equals 0. So if we plug in 0, we would have 2. So we would get 0, 2. And then once again, from graphing this, we would make an XY chart here. I'm going to plug in some points, -1, 0, 1, 2, and so on. And I'm going to even add in -2, because -2 is up at 8. -1 is up at 4, over 0 is up 2, over 1 is up 1, over 2 up 0.5, and then it just gets, the more you scroll down, the smaller and smaller it gets. It approaches 0. We have an asymptote at 0 because there's no shift up or down. And you can see it if you look at your calculator values that it's just getting smaller and smaller and it never goes to 0. So now plotting these points here, we're good almost. -2 up 8 units, -1 up 4 units, over 0 up 2 units, over 1 up 1, and then it's just getting smaller. By the definition of an asymptote, it's just coming down, getting close to this. So we'll connect those nice and pretty. Domain, -infinity to infinity, range, once again, 0 to infinity, not including 0. Okay. Change of base formula, guys, is log of the big thing divided by log of the small thing. So log of 12 divided by log of 4. It does say just to use this to rewrite it as a common logs, but we'll calculate it. The point of the change of base formula is to be able to type it into our calculator. So let's go ahead and calculate this. Log of that divided by log of that. Remember, change of base formula allows us to now type it into our calculator. It says round to, I don't know, let's just round to 2 decimal places. And then 7. Pretty easy stuff. Okay, it says a parent increases a child's allowance by 15% each year. If the allowance is $3 now, when will it reach 15? Notice it didn't say compounding continuous. Therefore, we must just be using our simple interest formula, a times b to the x, where this is our initial value, this is our growth factor or decay factor. In this case, growth. So our initial value is $3. That's how much the parent is paying their kid for their allowance right now. It's increasing by Now remember with our rate, sorry, I got interrupted there. Our rate would be 1.15, because with this one we do have to add the 1. So 0.15 is our 15%, 1.15, 100% of that $3 back plus an additional 15%. And we don't know how much time it's going to take for them in the end to get $15. There's two ways to solve this one. By calculator, where you graph it by doing y1, y2, and seeing where it intersects. Now, why do we have to do that? Because what we're trying to solve for is in the variable. The variable is in the exponent, is what I meant to say. If this wasn't in the exponent where we were trying to solve, then we wouldn't necessarily have to do it by calculator. It would be pretty simple algebra. But because x is in the exponent, the only way to solve is 1 by logarithms or 2 by graphing. I'm going to personally do logarithms, but I don't care how you solve it. A lot of you find it easier to just solve by graphing. You will get the same answer. So to solve this by logarithms, I have to isolate the base, so I would divide both sides by 3. So 5 is equal to 1.15 raised to the x, and I'd say I need to get x out of the exponent. So I'm going to undo base 1.15. So I log base 1.15 both sides, log base 1.15. That undoes that. So we have x is equal to log of 1.15 of 5. Now I need the change of base formula, so x is equal to log of 5 divided by log of 1.15. This is just the way I prefer because I don't want to pull out my calculator. It does not matter though if you were to graph it in y1, y2, see where they intersect. You would have a exponential, you'll have a line, you'll do second trace, see where they intersect. I'm doing it this way. So you should get 11.5 years. Don't worry about converting it to months for the test. Just the ACT will, so that's why we learned that. Okay, next one. So bacteria in a colony is 50. 2 hours later, she knows the number of bacteria has increased to 80. So we've got to start with that information to be able to figure out our growth factor. So notice we would be using this formula, simple growth or decay. So let's start out here. We know a lot of stuff. We know that in the beginning there was 50 bacteria. We know it was growth, but we don't know how much growth. And after 2 hours, it was 80. So now we can solve for B. So we would divide both sides by 50. Now don't say, I need to graph this. Guys, this is like easy. Like we can solve for B. We just need to square root both sides. This is easy stuff. So then if you type that into your calculator, you would get 1.26, roughly, a big long decimal equals B. I'm going to just go ahead and round right here, 1.26. So that's our growth factor, everybody. So now we can use that information because it says if it continues to grow at this rate, how much longer will it take for the bacteria to reach 100? Now, based on the wording of this, it's you got to be pretty careful because we're no longer starting at 50. It says how much longer from here will it take? So our initial values, we're starting at 80 now. So how long will it take if we start at 80 to get to 100? Our growth factor is 1.23 raised to the x. Now we're trying to find how much time. So notice in this one, the algebra is different because what we're trying to solve for is stuck up here in our exponent. We would need either to solve by y1, graph it, y2, graph it. You'll have an exponential, a line, you'll find where they intersect, or use algebra. So I'm going to do it with algebra. I would take both sides, divide by 80 to isolate my base, 1.2. Oh, I wrote 2.3, but it's 2.6. So we're going to fix that real quick. So 1.26 to the x. And then from there, I can say I am going to undo this base with a log base 1.26 both sides. This is just how I prefer, once again. That undoes that, so x drops down. And then we have log to the base 1.26 of, now 100 divided by 80 is just 5/4. So now we could use the change of base formula to solve this if this is the method you chose. So we would do log of 5/4, change of base formula, log of that, divided by log of that, divided by log of 1.26, and you get around 0.95. So 0.95 years, or I think hours is what we're looking at. So hours. 0.95 hours later, we would get to 100. Please though, if you really want, just solve by calculator. y1, y2, find where they intersect. which notice is very different than when we had to solve over here, because b was not an exponent, so it was just algebra. Okay. Describe the shift from the parent function. So right here, the parent function would be base 3 to the x, so it would be shifted up 1. And then this is a reflection over the x-axis. Over here, this is actually our parent function, log to the base 5 of x. So there's no shift left and right, no shift up and down, no stretch or compression. If we had this, y is equal to, for example, 2 log to the base 5 of x minus 3 plus 1, let's say we have that, then we could say, this is our parent function, we went right 3, up 1, stretch of 2. But notice, no shifts. None. So then right here we'd say, okay, our parent function is log of x, technically log to the base 10, we just know they don't write it. So there's our parent function, so then it was shifted left 1. So on the next page it says, you invest $500 in 2 different accounts. One interest is compounding continuously, and one is getting interest just annually. If you yield a 6% return in both accounts, which account will make more money? So remember, this is PERT, y is equal to p times e raised to the RT, versus simple interest, y is equal to a times b raised to the x, simple growth. So we know that if you're getting interest all the time, it's going to be higher than if you only get interest once in the year. So we can already say our compounding continuously interest rate will give us more. But now it says how much money, how much more. So it tells us if we put them in for 7 years, how much more money. So let's calculate each. First, I'm going to calculate PERT. So y is equal to, we put down 500. E, remember with PERT, you just change it to a decimal, but you don't add the 1. So 0.06 times 7. And the amount of money that they do have is $760.98. Now, if we're going to just get interest once in the year or just getting it annually, then we would have our formula $500. Our growth factor would be 1.06. We do need to change that one. Raised to the 7th. And we would get $751.82. So the difference turns out to be $9.16 difference, which notice isn't very huge. And we have talked about why. It is still better. Continuous was still larger, so a student wants to save $8,000 for college in 5 years. How much should be put into account that pays 4.2% annual interest compounding continuously? Notice compounding continuous. So you'd say y is equal to p times e raised to the RT and put in everything you know. A student wants to save $8,000. So that's what they want to end up with. 8,000 is equal to in 5 years. So our time is going to be 5 in a second. How much should be put into account if the account pays this much interest? So that would be 0.042, and then it was time 5 years. Now a lot of people think that they need to solve by calculator here, and you don't. This is p times e raised to all that stuff. So notice, to get p alone, what you're trying to solve for is p. Your variable is not stuck in an exponent. So we just have to get p alone. So we would divide by e.042 times 5 to both sides. Now, how come I know that works? Because then look, p is alone. If you type this into your calculator exactly as you see it, you're going to get $6,484.67. To get $8,000 in 5 years, you would have to today insert this much money. So that kind of makes sense. If you get this outrageous answer, then you've done something wrong. So think about it. Your answer should make sense because they're like real world problems. So notice we're not solving anything here. It's already solved. These are true statements. It just says write it in its logarithmic form. So you'd say, okay, this is my base because that's what's raised to the 3rd power. I need to write it as a log, so I need to undo the base. So I log base 7 both sides, 3 drops down, so then we have log to the base 7 of 343. Remember, it eats the other side. So then right here, we'd undo it by log base 2/3. So then over here it cancels out. Negative 3 equals log to the base 2/3, and then it eats 27 over 8. Over here, log base 2. So then these cancel out. Negative 4 is equal to log to the base 2 of 0.0625. It eats the other side. Keep in mind, I hate that they don't write parentheses around what's really trapped inside the log. So I go through and do that so that I don't make some errors that I might make otherwise. So we know that even though there's not parentheses written, it goes without being said that those are there. So writing these as a single logarithm. So first of all, notice you got to take care of your what's multiplied in front. So obviously, guys, two separated logarithms. We have the same base, so we can put them together. So we have log of, and then remember, first of all, we got to fix this. That's an exponent. So then now this is gone. When you subtract and you divide, this is positive in front. Therefore, this goes on top. So you have a 2 divided by 1 to the 3rd power, which obviously simplifies to be log of 2 in the end. Now look, one logarithm, always better than separated logarithms. So notice, log to the same base again, log to the same base, so we can put these together. Log of to the base 10. We know it's secretly base 10. When you subtract, then you divide. So we have a positive in front here, so A goes on top. Now we have a divide sign, then both of those things, A, B. Now notice there wasn't an exponent to fix here, so that's why I didn't have to do that. So obviously you should notice A's divide out. Don't magically float B up, that's a 1. So your final answer would be log of 1 over B. Then right here, people always get thrown off. 1/3 times all this stuff. You should be saying to yourself, oh, well, maybe I should distribute that in here and here, just because there's parentheses for a reason telling me to multiply to all the stuff inside. So now I'd say, oh, you know, I better fix those exponents. Anything multiplied in front is an exponent. Now you'd say when you add, you multiply. So we can now write 1 log to the base 4, put parentheses, 1 log base 4. Don't write out 2 log base 4s. 1 log base 4. Then we have an x to the 1/3 times z to the 1/3. Now remember, if you have a rational exponent, it's the same thing as a radical. So we would probably go like this. Log to the base 4 of the cube root of x and z. Both cube roots, so I put them under the same cube root. It says evaluate each logarithm, but it does say without the use of a calculator. So normally we can do the change of base formula, log of 27 divided by log of 3. Log of 1 over 81 divided by log of 3. However, because we're not allowed a calculator, I'm going to set it equal to x and rewrite it in its exponential form so that it's more easy to solve. So we're looking for 27 is equal to 3 to the what power? So you could solve this by trial and error, or you could get this as base 3. Well, 3 to the 3rd power is the same thing as 27. So we have 3 to the 3rd power equals 3 to the x power. Therefore, because these are the same base, we can now just conclude that x must equal 3, or, you know, basically, we're saying log to the base 3 of 27 equals 3. Our final answer is 3. So same thing over here. Let's rewrite it as an exponential. So 1 over 81 is equal to 3 to the what power. Now I just pretend like I'm solving this. 81 is equal to 3 to the what power. So you know it's 3 to the 3rd power, I think, is 27. So 3 to the 4th power is 81. If you didn't know that, you would test it out. So we have 3 to the 4th power equals 3 to the x power. Therefore, x must equal 4. Now don't forget, though, we pretended like it wasn't flipped over a fraction. So what flips it over a fraction is having a negative exponent right here. A negative would flip it down. So x is equal to negative 4. Or basically, log of the base 3 of 1 over 81 is equal to negative 4. I skipped these ones, but they're pretty easy. So I'm not going to do very many of them because they're literally the same step. Oops. So we're just using the change of base formula. It didn't specify, so if it doesn't tell me I have to solve it a certain way, I personally just do change of base formula. So we know we do log of that divided by log of that. So log of 125 divided by log of 5. And then yes, you would then type it into your calculator. If you do type it into your calculator, I believe you get 3. So then here, log of that, change your base formula, allows us to calculate this without having to rewrite it as an exponential. It's really the easier way because we don't have to think. And I think we get negative 1/2. But I did just do those in my head instead of doing them in a calculator, so hopefully I'm right. Okay, you put $2,000 in an account earning 4% interest compounding continuously. Once again, because of that special word, compounding continuous, and only because of that, we're using PERT. Now I write it down. Y is equal to PERT. Then I'm going to plug in everything I know. You put $2,000 in, so that would be a 2,000 right there in this problem. We have Y is equal to so far 2,000. E is E. Our interest rate is 0.04. And then it says, for in a time of 8 years, how much money did you earn? So this one's easy. It's just calculate straight across. So when you type that into your calculator, you will get $2,754.26. Alrighty, graphing this function here. So if we're going to graph y is equal to log to the base 2 of x, the first thing you would do is say, I'm going to rewrite this as an exponential, so I switch x and y. I'm finding the inverse, and then I'd say I need to undo base 2 because I need to get y alone, so I'm going to need to undo log the base 2 because I need to get y alone, so I'm going to base 2 both sides. So 2 to the x equals y. Well, we know how to graph that, so y is equal to 2 to the x. We're not going to graph it though, but we're going to write down that xy points. -2, -1, 0, 1, 2. I just picked some generic points around the origin. If I plug in -2, I get a fourth. If I plug in -1, I get a half. If I plug in 0, I get 1. If I plug in 1, I get 2. If I plug in 2, I get 4. Do not graph those points or you're graphing the exponential. We want to graph the log. So now all we have to do is take those xy points and switch them since they're inverses. A fourth, -2, 1/2, -1, 0, 1. 1, 0 is what I meant to say. I gotta give myself some room, so let's pick that down. Erase that. So over 1 up 0, over 2 up 1, then over 4 up 2. So I can start graphing those. So look, over a fourth, down 2 units. Now I'm going over a half, down 1 unit. Over 1 up 0, over 2 up 1 unit, over 4 up 2 units. Now think about it. So it's going to come up like this, and it's going out that way, and it's coming down in by this asymptote. So it's just going to continue to get smaller and smaller. Think about it over here. If we kept going this way, we would have got smaller and smaller. So logarithms have an asymptote, but now vertical asymptote at 0, because it was not shifted. This is a non-shifted, no shifts left and right, logarithm, which always have this vertical asymptote at 0. So now you could say my domain, because they're going to ask you that, domain is 0 to infinity, not including 0, since it never crosses this asymptote. And our range is -infinity to infinity. It's growing down forever, up forever. Now think about taking and shifting this graph. If I shifted it back 4 units, we would then take our asymptote back 4 units, and then let's say I shifted it up. It'd be somewhere up here like this. Notice the domain changes. If I shifted it left 4, we would be now -4 to infinity, but my range would not change. It would still be -infinity to infinity. Just making sure you understand, if we start shifting functions, our domain and range is pretty easy, as long as you think of what the original graph would look like. We're solving, so every problem is different. We solve exponentials and logarithms by isolating the log or isolating the base. Now, keep in mind, so looking at this one, we have to get 3 all by itself. So I'm going to subtract 8 from both sides. So I have -3 raised to the x equals -9. You cannot undo base 3 unless it's completely alone. So I got to divide both sides by -1. Base 3 to the what power equals 9. So now I could do this a couple different ways, but keep in mind, most of you will then log base 3 both sides, log base 3. So then we would have x is equal to log to the base 3 of 9, and it would now take the change of base formula, so I can actually input that into my calculator. So log of 9 divided by log of 3 equals 2. X equals 2. We could check our answer by plugging it back into the original. So if you go in your calculator and type 8 minus 3 to the second power and hit enter, you should get -1, and you do. So solving this logarithmic equation, you would say, I need to isolate the log. Now keep in mind, 81 is trapped inside. So you'd say, get the log completely by itself. Well, in this problem, it happens to be completely by itself. So now we would undo. Oh, there's so many ways to do this. So we could do base 3 to both sides. Log base 3 and base 3 cancel out. 81 equals 3 to the what power? So then you could go through and trial and error, see 3 to the first. Does 3 to the first work? Does 3 to the second work? No, no. And so on. 3 to the third is 27, so no. 3 to the fourth is 81. So our answer must be 4, x equals 4. But there was an easier way. We could have just used change of base formula. Because it says log of the base 3 of 81 equals x, so we literally could have done log of 81 divided by log of 3 in our calculator. Okay, so looking at this one though, notice we'd say so those are parentheses are already there. You'd say I need to solve for x. It's trapped inside log. I need to undo log. Well, I can't undo log because there's two separated logs by a subtraction sign. You can only undo a log if there's one log on each side of the equation or one on this side. But you wouldn't want to bring this over because then you're going to have a 2 added. So instead you're going to put these logarithms together since they have the same base. When you subtract, then you divide. So let's write this as one log. So we have log of x divided by 3 equals 2. And now because we only have one logarithm, we can undo the log by base 10ing both sides, since this is secretly a base 10 right there. Base 10 and log of the base 10 cancel out. X over 3 equals 10 to the second power. Base 10 raised to the second power is 100. So then to get x alone, we times up by 3, so x equals 300. And we could actually check that answer as well. If you go back and type in your calculator, log of 300, since it was base 10, we can do it really easily. Minus log of 3, if you hit enter, you should get 2. So it says, describe how this is comparing to the parent function, and then state the domain and range of this function. So you would say to yourself, well, the parent function is log to the base 2 of x. That would be the same logarithmic equation, but with no shifts. We've now shifted right 3 units, and then down 4 units. That's our shift. Then from there, you would say, okay, domain and range here. Well, if you think this is going to help you, if you think about what this is, asymptote is normally at. So this one's graph with no shifts has normally an asymptote at 0. And it looks like this. So now we're taking that and we're shifting it right 3 units. So if I go right 1, 2, 3 tick marks, there's my new asymptote. And then we're shifting it down 4 units. So this is literally just like shifting down. So I'm only drawing a rough sketch to help me with domain and range. So now if you look at this, the only thing that changed is our domain. Because no matter what, it's still going to go down forever and up forever. So our domain now is actually 3 to infinity, not including 3. Our range is still negative infinity to infinity. So this says what property is being used here. So we know if we have 2 logarithms that are both the same base and there's a subtraction sign, we can put them together with a division. So log of the base 6 of 16 divided by 4. So it says what rule was used? The division rule. Better used in math as quotient rule. But whatever. Division rule, I get that you know what you're doing if you write division rule. So then this one, notice, once again, you can't put these logs together until you fix the exponents. So we have log to the base 2 of 3 squared plus log to the base 2 of 4. And now because we have just a log base 2, we can put it into one thing here. So 1 log base 2. So then we would have 3 squared times, when you add, you multiply, times 4. So the rules that were used here was the power rule to fix the exponent, and then also the multiplication rule. When you add, you multiply. Identify each function as linear, quadratic, or exponential. So A is this. We would say this is exponential. So why? Well, what makes something an exponential function? The only time we have an exponential function is if x is up in the exponent, and it is. So this one is quadratic, obviously, because it's degree 2. then this one is linear. Obviously, because it's degree 1. So that's your explanation. So when it says calculate, you literally type into your calculator ln of 5.2, you hit enter, and you should get 1.65. It says, is this exponential growth or decay? Find the y-intercept. So because 0.85 is less than 1, it's decay. And then our y-intercept is when, once again, x equals 0. So 0, comma, if I plug in 0 right here, that becomes a 1. So it's 0, comma 4. Then right here, we would say this is growth. 1.03 is larger than 1, so it's growth. Then our y-intercept is when x equals 0. Sorry, I didn't mean to write that. So 0, comma, if I plug in 0 here, that becomes 1. So 0, comma 18. Pretty easy stuff. So then right here, once again, this one would be growth, because 2.25 is greater than 1, so it's growth. And our y-intercept would be 0, comma 9. You're getting the picture of how to do this. Hopefully you got all that. I do not know if this was recording. So real quick, we know this one is decay, growth, growth, and then I just plugged in 0 for x to find my y-intercept. You plug in 0, that becomes a 1. Therefore, we would get 4. So notice 0, 18 and 0, 9. Because if you plug in 0 here, that becomes a 1. This says solve each equation, round answers to the nearest 10,000. I want the pretty answer as well. So we're going to say, okay, do not undo this base until it's completely by itself. So you would add 9 first. So we have 3 raised to the n plus 2 equals 16. Now you can undo it. So now we do log base 3, log base 3. So we would have n plus 2 is equal to log to the base 3 of 16. Well, we got to rewrite that. It's the change of base formula. So log of 16 divided by log of 3. And then our last step to get n alone is to subtract 2. So n is equal to log of 16. This is the pretty answer that I would want. Log of 3 minus 2. Then when you type that into your calculator, you should get 0.5237. So over here, you have to get the base by itself. So I'm going to divide both sides by -4. So then I have base 16 raised to the 7p equals, and if you do that in your calculator and hit math, enter, enter, you get 19/2. And now you say, okay, I got to undo base 16, log base 16, log base 16. 7p equals log base 16 of 19/2. So then we would do the change of base formula. So we have 7p equals log of 19/2 divided by log of 16. Then divide by 7, and p is all by itself. There's the pretty answer, and if you type that into your calculator correctly, you should get negative 0.1160. So doing this first one here, it says use properties of logs to solve the following log equations. So what they mean by that is we can't solve for x, we can't get this out of the logarithm unless there's only one logarithm. So we're going to use properties of logs to put these together. But first, we've got to take this 2 up into the exponent here. So we have log of 5 squared plus log of x equals 2. So now you'd say, well, I can put these logs together. So we have log of 5 squared times, when you add, you multiply, times x equals 2. So that's log of 25x equals 2. So now that you have one logarithm, you can undo the logarithm by applying the correct base. We know it's secretly base 10. So when we base 10 both sides, those cancel out. So we have 25x equals 10 squared, which is 100. Therefore, x must equal 4. And if we check our answer, that would be plugging it back into the original. So we would have 2 log of 5 in our calculator plus log of 4. If you hit enter, you should get 2, and we do. So for this problem, we would not be able to undo the logarithms unless there's one logarithm. So when you add, you multiply. So we would have log of x minus 21, and then that's all times by x. That's equal to 2. So now you'd say, okay, I can undo log base 10 by base 10ing both sides. So then that cancels out with that. So we have x minus 21 times x equals 100. 10 squared is 100. So then from there, we would say, how do we solve this? Well, don't be mistaken. Remember, this needs to be multiplied in. So x squared minus 21x equals 100. You'd say it's a quadratic. I solve quadratics by getting them set equal to 0 and solving by factoring or quadratic formula. We do not use the quadratic formula if it can factor. So I subtracted 100 to get it set equal to 0. I go off to the side. What multiplies to be a times c adds up to be b. What multiplies to be negative 100 and adds up to be negative 21. So 25 times 4 and negative. Then we can quick factor. So this factors to be x minus 25, x plus 4. Don't be the person that says that that's your solutions. Guys, factoring is just putting it in a different form to make it easy to solve. Therefore, x equals 25, x equals negative 4. So then we would just check both of those answers. So 25 and negative 4. Let's look here. So we have x equals 25 and x equals negative 4. So if we plug in, notice if we plug in 25, it stays positive. So if we plug in 25 right there, it stays positive. If I plug in 25 there, it stays positive. So there isn't a problem. But notice when I plug in negative 4 right there and right there, there's a negative inside of a logarithm, which cannot happen. Therefore, that's an extraneous solution. We would only keep 25. I don't know if the video, I don't know what the heck. I don't know if the video recorded on this last one real quick, so I'm going to do it super quick again. Sorry if it did record, but I don't think it did. So we would have to put these together. So we would say, oh, I got to fix that. That's an exponent. So we would have 5 squared, which is 25. So now when you add, you multiply. So then we would have 25 times, so we add, you multiply, times x equals 2. So then we base 10 both sides to undo the log. 25x equals 100. Therefore, x equals 4. That's how you would do that first one. So keep in mind this is trapped inside. You can't undo the logarithm without having one logarithm. When you subtract, you divide. So we could put this together. 4x divided by 5 equals 3. And now undo log base 10 with base 10. So 4x over 5 equals 1,000. Then you say, I got to get solve for x. So now I'm going to multiply both sides. Wow, having issues here. So I'm going to multiply both sides by 5. So then we have 4x equals 5,000. And when we divide both sides by 4 now, we get x is equal to 1,250. Expand the logarithm. So this is really in parentheses, keep in mind. So you'd say, okay, I'm going backwards. I'm splitting this apart. So when you divide, you subtract. So I have log to the base 7 of 8 to the 6th power minus log to the base 7 of 5 to the 6th power. And if we're expanding that, then we should be bringing our exponents down here. 6 log to the base 7 of 8 minus 6 log to the base 7 of 5. So with this one, when we go to expand it, the first thing I like to do is say, well, I'm going to be breaking this apart. I know I'm going to be bringing my exponents in front. So I'm going to just go ahead and put 2 in front there and there. I'm going to like distribute it is what I'm trying to say. So we have log to the base 2 of actually really 8 squared divided by 7 to the 6th power. So now when I expand this, I'd say when you divide, you subtract. So we have log to the base 2 of 8 to the 2nd power minus log to the base 2 of 7 to the 6th power. And then if we're expanding this, those exponents will come in front. 2 log to the base 2 of 8 minus 6 log the base 2 of 7. So that would be expanded completely. I'm going to skip the next part, problems 28, just because it says evaluate. Well, use the change of base formula. It's super easy stuff. You would do log of 81 divided by log of 9. Log of 4 divided by log of 64. Log of 8 divided by log of 4. So we've done enough of that stuff. Let's go on to 29. Condense each expression to a single logarithm. So we're doing this again. First of all, we have to put the log base 5s together. Well, we cannot do that unless we've taken care of the exponents. So we would have log to the base 5 of 7 to the 6 minus log to the base 5 of 2 to the 24th. And then it says put it as one logarithm. When you subtract, you divide. So you go like this. Don't write 2 divided logarithms. That defeats the purpose. We only want one log written. So we have log to the base 5 of 7 to the 6 was positive in front, so that's going to be on top. Subtract 2 to the 24th power. And yeah, we could calculate that, and see what happens, but that's good enough because we've answered it. Condense it to a single logarithm, and that's good to go. Now notice they don't once again write parentheses, but we know that they're really there. Sorry about that. We know that they're really there, so I throw them in. So we can put the ln's together as long as we take care of the exponents. Do not take the negative up. So we have ln of 12 to the 4th minus ln of 11 to the 4th. Now when you subtract, then you divide. So we have 1 ln, on top would be 12 to the 4th divided by 11 to the 4th. And that is putting it into one logarithm. And yeah, we would simplify on the test if it wasn't some outrageous number inside. So you could type into your calculator 12 to the 4th and then divide it by 11 to the 4th and hit math, enter, enter, and see what happens. So what we're going to do, oh, I don't want you watching, is do the change of base formula again here. I don't really think we need to continue to go over this and over this, but the reason I keep circling back is so that you keep seeing things and then seeing them again after you see other things, so that you really know what you're doing and you don't get to the test and say, now which one was this? You're so used to switching back and forth and seeing things randomly placed that you're good. So this one would be 1.8927. We would do log of 4.6 divided by log of 3. I'm only going to do those two on that section because we get the picture. If you can do these two, you can do them all. Also, a side note, I'm not going to do 31. 31's answer, if you did do it, you get this answer correct. So I'm not going to go through that one. That one's not a big deal. So we're going to move on to the back page here. So now we are on the very back page, problem 32. So when it says solve, you'd say, okay, I need to isolate the logarithm. So notice on this side of the equation, there's nothing added or subtracted, so we're good. And then over here, nothing added or subtracted. So our logarithms are isolated. So now we can undo this log base 7. So I'm going to base 7 both sides of the equation. So that undoes that. So then we have 5n plus 6 drop down. Well, this happens to undo this as well. So we have equals n plus 9 drops down. And then it's just a linear equation that we just need to solve. 4n plus 6 equals 9. So then we have 4n equals 3. So then n equals 3/4. Don't do it in your head. A lot of you do it backwards. Like actually go through and divide by 4. So you don't actually write 4/3. A lot of people do that. Okay. This one's 33. So it says it gives a big old spiel here about friends debating about how functions work and which graph is correct. So I'm just going to talk about what this graph would look like. We know it's a shift of right 3, down 1, and then it's actually a reflection over the x. So reflection over x-axis. So we know it's going to be right 3 units, down 1 unit. So we are going to have an asymptote at -1. And then where it's reflected, normally an exponential looks like this, but now it's reflected, so it's going to be like this. It's reflected over the x-axis. So imagine yourself flipping that down, And if this was down here, it'd flip down and head this way. So then the graph of this, oh, what did I do wrong? Let's see. So, normally, oh, it's just the shift that's throwing me off. I didn't shift it. So we said right 3 units, which is true. So, and then down 1 unit. Well, I can already see based on this asymptote that the bottom function is right. So normally it looks like this. Oh, but it's decay. So that's why. No, it's growth. Anyways, I know which function it is. Based on the shifting alone, it's got to be this one. And we can even type it into our calculator and kind of see what's happening. So I'm just bugged. I'm just thinking about an exponential looks like this, and then we flip it, and then, yeah, it was shifted. That's what's throwing me off, the shifting. So it'd be the bottom person. I don't know. It's hard to say with 33 of which person's Don, and the other one that was wrong was up here, like this. This was the wrong person because of the shifts of the graph, because it was down 1. And it looks like they went up 1. They have an asymptotic positive 1. So right here we would be, I just kind of summarized this because you can read it off the review. We have log of I1 divided by I2 equals magnitude 1 minus magnitude 2. So it says, how much more intense will Utah's earthquake be than the earthquake that happened in Idaho? So we have log of I1, I2, and then our magnitude 1 is 8. Magnitude of the second earthquake, 2.4. I always put the positive one first. You should too. So then we have log of I1 divided by I2 equals 5.6. And then you say, I'm trying to get in how intense, how much more intense. That means I'm trying to solve for I. And really it says how much more intense is the first earthquake. So we're really solving for I1. So now we'll base 10 both sides. Don't do 10 times 5.6. It's 10 raised to the 5.6. So then I1 divided by I2 is equal to 398,107.17. And then think about it. To solve for I1, we would multiply both sides by I2. So then I2 would cancel out. So look at what this says. The intensity of the first earthquake was this much more intense than the this one was this much more intense than the second earthquake. Because it literally says this much times as intense as this earthquake. That's way, way more intense. We better hope that that is not true, that we're not going to get an earthquake of magnitude 8, because that could cause a lot of damage. All right. Last one. So easy. It says, a student wants to save $14,000 for a new car to use after they graduate from college. How much should be put into an account that pays 3.4% annual interest, compounding continuously? PERT again. Only use PERT if you have the word compounded and continuously together. So now put in everything you know. They want to save, in the end, they want $14,000. They don't know how much they need to put into the account. E is always E. 0.0, our rate is 0.034, then times 4. Now, once again, every problem is different, so algebraically, how should we be solving for this one? You're trying to get P alone. This is another one where all we have to do to get P alone is divide by E 0.034 times 4 to both sides. And then you've reached your goal in this one, P's alone. When you type that into your calculator, it would be $12,219.80. That's how much you have to put in the account to have $14,000 to buy a car with in 4 years.